Hi there, I'm Peter. This is joint work with Pavan and Vinod. We're going to be presenting our complete problems for multi-pseudodeterministic computation. So what we have is some natural problems that are, in a sense, complete for pseudodeterministic computations. What we mean is if these problems have pseudodeterministic algorithms, then lots of other problems also have pseudodeterministic algorithms. So first I'm going to explain what exactly pseudodeterminism is, and then a generalization called multi-pseudodeterminism, and then explain what exactly our completeness result says and how we get it. So we're going to be focused on search problems and function problems. So we've got problems with multiple correct outputs. You want to compute one of them. So we're going to use Sx to denote the set of acceptable outputs for a particular input x. So like as an example, we want to generate prime numbers. So you get 1 to the n as an input, and you got to generate an n-bit prime. If, like, let's say n's 4, then Sx would be 11 and 13, because those are the 4-bit prime numbers. Or you want to find non-roots of some big polynomial. Their Sx would be the set of all things that aren't roots of that polynomial. And so both of these problems, there's fast random algorithms where you basically pick something at random and then test to see if it's in Sx. The downside is each time you run it, you might find a different element of Sx, and sometimes that isn't what you want. Like, you know, that algorithm for here n equals 4, half the time you'll get 11, half the time you'll get 13. So, like, let's say you're in a distributed computing setting, you know, you might want every process to agree on a particular prime number. And so this motivated the following definition. We say an algorithm is pseudo-deterministic if for each input there is a like canonical output that we find with at least 2/3 probability. This is just like a simple diagram where, like, imagine these are the different random strings, and then the blue letters are the elements of Sx, the acceptable outputs. This one isn't pseudo-deterministic. It's still a fine algorithm for the problem because you get a good answer 3/4 of the time. But what we're looking for is a pseudo-deterministic algorithm that will always output the same thing. So one other reason that pseudo-determinism is kind of neat is suppose p equals BPP. That is, like, we can de-randomize every BPP computation, make it fully deterministic. That doesn't immediately de-randomize search BPP. There can be random function computations that don't get de-randomized for free by this, as far as we know. It's not known either way. But de-randomizing BPP is equivalent to making all pseudo-deterministic algorithms deterministic. And one thing I should mention is that decision problems are kind of trivially pseudo-deterministic. So pseudo-determinism kind of connects search to decision problems in this way. So here's some of the prior work on pseudo-randomness. The paper that defined it gave a couple of neat pseudo-deterministic algorithms. Gatt and Goldwasser showed that you can do you can find generators for some cyclic groups. You can find non-residues and non-roots of polynomials pseudodeterministically. Goldwasser and Grossman showed that you can pseudodeterministically construct a bipartite perfect matching in randomized NC. You can, if you could pseudodeterministically estimate the size of an NP language in BPP with an NP oracle, then we'd get some new circuit lower bounds. That's how we sort of got into pseudodeterminism. It's possible to generate primes pseudodeterministically in sub-exponential time at infinitely many input lengths. That was shown by Oliveira and Santanam. And then Goldwasser, Grossman, Holden considered pseudodeterminism for interactive proofs, and Goldwasser, Grossman, Mohanty, and Woodruff considered pseudodeterminism for streaming algorithms. So there's a lot of places and ways you can apply this concept. All right, so now it's time for our results. So we're going to start by discussing pseudodeterminism for approximation algorithms. So an approximation algorithm, we've got a function that outputs an integer. We want to compute f of x, but sometimes that's hard, so we'll settle for getting close to f of x. There's two different ways you can measure this. You can consider a multiplicative approximation. That means that you're off by some factor that's based on this epsilon, or an additive approximation where you're like within plus or minus epsilon. And what we'd like is to get pseudo-deterministic approximation algorithms. And it's easy to get really close. You can make every approximation algorithm, you can narrow it down to one of two values. And the way you do this is you pick some thresholds to round to. So if it's from here to here, we round up to the blue line. If it's here to here, we round up to this blue line. And if it's here to here, we round up to here. So we pick the size of the intervals so that our approximation error can't contain more than two blue lines. And that means that, wherever f of x is, it'll either get rounded to one line or the next line. But you can't have something that gets rounded to this line, something that gets rounded to this line, something that gets rounded to here, no matter where f of x happens to be. So that motivated Goldreich to define multi-pseudodeterminism, where instead of a canonical solution, we have a canonical set of size k. And we land in the canonical set with probability k plus 1 over k plus 2. And this is kind of a natural analog of the 2 over 3 for pseudodeterminism. And it's actually very important to have this because we don't know how to amplify this probability if it starts out below here. If it's at least k plus 1 over k plus 2, we can do standard amplification techniques. We run it a lot of times and output the most common value. But if you drop below this probability, then there could be a bad output that's more likely than any individual good input. And this is actually also closely connected to some earlier work by Grossman and Liu. They considered this idea of reproducible algorithm, where you have a two-part algorithm. The first part uses randomness to generate a string, and like a k-bit string. And the second part kind of behaves pseudodeterministically once you give it the k-bit string. And then in the multi-pseudodeterminism paper, Goldreich showed that these are equivalent, like order k reproducible is equivalent to 2 to the order k pseudodeterministic, which makes sense because if you could have like 2 to the k different strings, and then that kind of fixes what your canonical set is. All right, so our completeness result. The complete problem we consider is estimating the collision probability. This is an approximation problem, so it's too pseudodeterministic. And we've got a circuit with a 1-bit output. We want to estimate the chance of getting 0 twice or getting 1 twice on a random input. And we proved that this is complete for approximation algorithms in the sense of like the context of pseudodeterminism, in the sense that if you can make this pseudodeterministic, you can make any approximation algorithm pseudodeterministic. So we start with an approximation algorithm, we make it too pseudodeterministic, and now we've got 2 things that we might get. We could get A or B, and we want to get rid of one of them. We know that the chance of getting A or B is combined at least 3/4, but we don't know how likely A is versus B. So one way we could try to get rid of one of them is we run a lot of times and we take whichever one occurs more often. If there's a gap in the probabilities of getting, like if A is more likely than B by some decent gap, then this will work very well. But if A and B are very close in probability, this won't be pseudodeterministic at all. On the other hand, we could try to run A until we know both good outputs, and then pick, use some arbitrary tiebreak rule, like we'll take the larger of the 2. But this one isn't going to be pseudodeterministic if we have a low chance of seeing one of the values. So like if you think about it, like as we run, like let's say we run A 20 times, B, and that just happens to be where we have a 50% chance of getting B after running A 20 times. And then that gives us, we'll output A unless we see B. And then it's not pseudodeterministic. We've got a 50-50 chance of outputting A or B. So what we want to do is combine the 2 strategies and use our collision probability estimator to pseudodeterministically choose between them. And this works because if A and B have very close probabilities, it's kind of more uniform, so we get a lower collision probability. And if one of them is really rare, then we're going to collide on B a lot. So estimating the collision probability, that's how we decide between the 2. And we need the pseudodeterminism on the estimation, because otherwise we might get an input where we pick strategy 1 half the time and strategy 2 the other half. Alright, so here's a little depiction of the algorithm. Let's just assume A is the less likely one, so it's got probability between 0 and 1/2. And let's say up to here, A is too small to see reliably, so the second strategy is bad. Up here, A is too close to B, So strategy 1 is bad, and then in this big middle section, both are perfectly fine. But we can't measure probability of A directly. We measure the collision probability. So there's some uncertainty when we do that, like so what we want to say is that if the collision probability is up to here, then the probability of A is at most here. So up to here could be bad, and up to here could be bad for strategy 1. And then we set our threshold right here, and we need our estimation error to be small enough that if we're to the right of the threshold, we can't possibly land in the red zone, and if we're to the left of the threshold, we can't possibly land in the yellow zone. And that means that if we're to the right of our threshold, then strategy 2 is perfectly safe. And if we're to the left, then strategy 1 is. So here's that idea written out as an algorithm. You build the circuit that simulates A of X, you estimate the collision probability of C of X, and the threshold we pick is 34 over 64. There's a lot of flexibility, though. You can play around with the constants quite a bit. And here's our strategy 1, strategy 2. And here's the numbers on why this works. So let's say we're in the bad case on the right, where the two have very close probabilities. So if they're at if they're within 2 epsilon of each other, then both of them have to be below 1/2 plus epsilon. And then the collision probability is bounded by the chance of getting A twice plus the chance of getting B twice, which is like, it works out to 1/2 plus 2 epsilon squared. On the other hand, if one of them is, like, if A occurs less than epsilon of the time, then the chance of getting B has to be at least this, because A plus B is at least 3/4 of the time. So that gives us a collision probability lower bound of 9/16. And then if our estimate is tight enough, and this error we pick here is tight enough, we'll always choose a good strategy. And we can kind of, we just decide on what epsilon we want to deal with beforehand, and that affects how many times we have to run A. So if, like in this case, we need to run A, like, maybe 2 epsilon times to have a good enough chance of seeing A. And we can pick, we can run it a lot if we want a really good chance, and so, yeah. And then it's easy to see that the whole thing will be pseudodeterministic, because everything after picking the strategy happens with very high probability, and we pick the strategy pseudodeterministically. So that's not the only complete problem we get. We also show that estimating the entropy of a circuit, Shannon entropy, and estimating the probability of getting 1 from a circuit are also complete. Because if you can do either of these pseudodeterministically, you can do collision probability estimation. So we want to consider this, push this beyond just approximation algorithms. So we're going to talk about multi-valued functions. That's just a very general concept where f of x is an arbitrary set. And about search BPP. Here we've got a relation R, and we need a probabilistic algorithm that outputs, like kind of find solutions to the relation, at least 2/3 of the time. And the key difference is we also need to be able to check that a pair is in the relation with like 2/3 success rate. That is like the relation is kind of a BPP decision problem. So first, for multi-valued functions, we showed that if there's a pseudodeterministic algorithm to estimate collision probability with small enough error, then any multi-valued function with a constant pseudodeterministic algorithm can be made fully pseudodeterministic. So collision probability estimation is complete for constant pseudodeterminism multi-valued functions. And we kind of take the algorithm for the approximation algorithm case, and we modify it to work for like a generic k to k plus 1. You basically just have to change the constants around, make some of them smaller, run it like k times as much, and each time you go from k to k minus 1, it increases the runtime by like, you take the runtime to like the power of 4 times some other constant. So the runtime grows really fast, but as long as you only do it a constant number of times, it's still polynomial time. For search BPP, the result we have is that if there's a pseudodeterministic approximation scheme for acceptance probability, then you can make any search BPP algorithm fully pseudodeterministic. This isn't a completeness result in the same sense because we don't have a verification procedure for acceptance probability, so it's not a search BPP problem. But how we do this is prefix search. So for input x, 2/3 of the random strings have to be good. So by conditional probabilities, either 2/3 of random strings starting with 0 are good, or 2/3 of the random strings starting with 1 are good. So first we'll check with 0. So we fix the first bit, we estimate this probability. If it's at least 2/3 minus epsilon are good, we'll keep the first bit being 0, otherwise we'll keep the first bit being 1. And epsilon is the error on our acceptance probability estimator. So we move on to the next bit, and we're going to lose epsilon each time we do this. Because if we kind of underestimate the probability, we have to take one of these. And so the best we can do is shrink it by epsilon every time we fix a bit. So that gives us this constraint that the length of the random string times epsilon has to be less than 2/3. But as long as we end up with a positive value at the end, the string has to produce a good output. If our estimator gives us a pseudodeterministic, gives us the canonical solution every time we run it, then the algorithm's behavior is basically deterministic. I mean, we get our estimate, all we do is we look at it and decide which value to keep. So the probability of getting the canonical random string out of this is the chance of our acceptance probability estimator giving the canonical solution every time we run it. And since we can just amplify that probability as big as needed. Yeah. So where can we go from here? One thing is, what other problems are complete? Can we get completeness in other settings? Like people have considered pseudodeterminism for streaming. Can you make a completeness notion in that sense? Can we get a complete problem that's actually in search BPP? And this was actually discussed in this paper by Goldreich, Goldwasser, and Ron, where they gave a semi-complete problem that was also not in search BPP. And last, are there search problems that don't have pseudodeterministic algorithms? Can you get that by could you prove that if you assume P is not equal to BPP? Because obviously if P is equal to BPP, then, yeah. All right, that's everything. Thank you for listening.